All right. Good morning, everybody. Hope everyone enjoyed the dinner and Lena's presentation at the planetarium last night. I always get super jealous when I see an astro presentation like that because my field doesn't have any cool-looking pictures like that. All right, so we're going to start this morning's session first off with Costis Papageorgakis. That may very good. Close, yeah. He happens to be head of physics and astronomy at Queen Mary University of London. His research focuses on machine learning for supersymmetric, superconformal field theories and string theory, and I believe that is what you'll be talking about with the bootstrap, so take it away.
Great, thank you, Mike. So good morning, everyone. Thank you for making it for the 9 o'clock slot, which is always a little bit of a problem. Today I'm going to be talking about machine learning inroads into the bootstrap program, which I'm going to be explaining to you. And this talk is loosely based on the following series of papers of the last few years with my outstanding collaborator, Vasilis Niarchos, who is a professor at the University of Crete in Greece, and a series of postdocs and students from Queen Mary and from Crete. I would like to give a shout out in particular to Alex Stapleton from Queen Mary, who's going to be graduating next year, and he's going to be on the market for AI for physics and physics for AI. And also Alex Stratoudakis, who is a master's, he's finished his master's at the University of Crete. He has been contributing at the level of an advanced PhD student, if you ask me, so he's fantastic. And the thing that is even more impressive about him is that throughout his undergraduate and master's studies, he's also an active, fully working firefighter at the front line. Just if you see an application from him, make sure to check it out next year. Okay, this is disagreeing with me, so let's go. Fantastic. Okay, now it works. Fantastic. So let me start with some motivation behind this work. We heard yesterday already from Socrates that AI tools obviously are finding numerous applications to many aspects of physics, and we've heard many, many different talks of great sort of breadth and quality in this workshop already. But adoption in high-energy physics, and more particularly in high-energy theory and formal high-energy theory, has been lagging compared to other fields. If you'd like an analogy, it's like we were a little bit late to the party of machine learning, and so much so that there's some people who are kind of asking themselves whether this is a party that is worth going to. But some of us have been to that party and are having a great time. So the kind of point that I would like to try and make to my community is that there's wonderful things happening. We need to find some kind of killer application that's going to make people interested in applying these tools and not kind of miss out on all these fantastic advances. There are very good reasons why this is a problem. And generically, we are a field without a lot of data. In fact, a field where there is not a lot of numerics. So what is the guide for doing research? It is mathematical rigor, and analytical results are the norm. In fact, it is not unsurprising to have a workshop of this size and have the talks being chalkboard talks. So if you'd like to kind of also talk about non-research objective specific applications of ML, but more broad applications of ML, even they were lagging behind. Applications of LLMs to our field of HepTH are not abundant. It is an interesting combination, I'd say, between pure maths and physics, because it relies on math reasoning and physics intuition, but there is not a lot happening there. We'll hear a talk about TP-Bench tomorrow, I think, by Moritz Munchmeyer. And we also had a paper that I'd like to plug last week about trying to fine-tune some foundation models on the HepTH archive as a set of first steps. So to summarize, the challenge that we have in HepTH is to find a suitable problem where machine learning techniques are going to make a difference, are applicable, appropriate, and are going to kind of give us something to look forward to. And in my opinion, the bootstrap program, which I will explain, is a prime candidate for this kind of approach. So this is the outline for the rest of the talk. I will describe for you the bootstrap philosophy. I will talk about the formulations of the bootstrap program in the primal way and in the dual way. Currently, the dual bootstrap is the one that is very popular and very successful in this field. And then I will try and explain how some ML-enhanced version of the primal formulation is tractable and can produce results which are competitive with those of the dual bootstrap. I will finish with 2 case studies and show a couple of plots for 2 particular examples of a one-dimensional CFT at 0 temperature and a 4-dimensional CFT at finite temperature. I would also like to say that in our field, we have an image problem in the sense that we have no images. And that is a problem that makes these talks a little bit monotonous. But we compensate for this by asking questions during the talk, which other fields do not do. So I would like to encourage you, and if the chair also agrees, to kind of interject your questions during the talk, and I'll make sure I'll finish on time. So my colleagues who are HepTH people know that this is the case, and I'm sure they will assist if some clarification needs to be made. This is a very broad audience, so I'm sweeping lots of things under the rug. Great. So the bootstrap philosophy is the following. This is an idea that goes back to the 50s and 60s. The idea is that if you've got a set of consistency conditions in your theory, they might be enough to completely determine the solutions to your physical problem. This program went under the name of the analytic S-matrix program, and the idea was that if you can use analyticity of the S-matrix, the scattering matrix of your quantum field theory, unitarity and crossing, you might be able to observe and constrain all the observables for strong interactions. That's before the advent of QCD. It turned out that this was not the case. It was too ambitious a problem in the program, and then QCD came along and provided a much more systematic framework for studying the theory of strong interactions. But the version of this idea has been used to great effect in a modern incarnation of the bootstrap with applications to conformal field theories. So conformal field theories are quantum field theories that are invariant, as the name suggests, under conformal transformations. Conformal transformations you can think of as extensions of the Poincare group that involve changes of scale while preserving angles. CFTs are ubiquitous, so they are the theories that are invariant under these CFT conformal transformations are fixed points of the renormalization group, so they appear and govern the behavior of QFTs in the ultraviolet and IR fixed points of the RG flow. They appear in the study of critical phenomena and even in the study of quantum gravity via what is known as the anti-de Sitter CFT correspondence, which is one of the most spectacular things that have come out of the formal HepTH community in the last 25 years. That says that a gravitational theory in d+1 dimensions on an ADS background is containing exactly the same physics as a conformal field theory in 1 dimension lower on the boundary of that space. And you find different ways to kind of study the physics of a gravitational theory via a quantum field theory in flat space and vice versa. So since these theories are quite constrained because of this, the fact that you've got these conformal transformations, we are hoping that they are more tractable in terms of a solution compared to general QFTs, and they are obviously of great interest in quite a few fields of physics. So let me now try and describe what the problem that we'd like to attack is in the conformal bootstrap application that I have in mind. The observables of a CFT are correlation functions of operators. They might be local operators. They might be extended operators. Here I'm thinking about some local operators. And the prototypical example is one with 4 operator insertions. There is a couple of ways in which you can try and compute this correlation function, and this gives rise to 2 results which are seemingly different but have to be the same. Equating these 2 results gives rise to a set of consistency conditions, which are known as the crossing equations. Formally, this goes under the name of operator product expansion, or OPE associativity property. And you get an equation that looks like this, which is a little bit of a mess. So we'll explain what the cast of characters is here, because this is going to be my objective function that I would like to try and solve using also machine learning techniques later on. So we'll call this thing function E. It is a continuous function of one complex parameter, Z. It also contains some data. The deltas here are the scaling dimensions of the operators that appear in this equation. L are the spins, and then C's are certain coefficients that multiply these functions here, which are very nonlinear functions of these deltas and L. So these contain combinations of 2f1 hypergeometric functions and so on. So what are my unknowns here? My unknowns are these coefficients C that appear in these 2 channels of the crossing equation. The scaling dimensions delta and the spins LK, which characterize the operators OK that I sum over in these 2 sums. And I have to make some very important clarifications here. First of all, these sums are unconstrained. They run over an infinite set of operators. So there's one problem there, because I have an infinite number of unknowns to solve for. But also the dependence of this function on Z and Z bar is continuous on this complex plane. So I have also a continuously infinite number of equations that I need to solve. If I knew all this information, I would, in principle, be able to compute any correlation function in my CFT, and as a result, I would have solved my theory completely. The thing to note here is that this is a completely non-perturbative formulation of the problem. It does not rely on a Lagrangian, and that's why this idea is very powerful. So because of the dependence of these functions here on delta and L, the resulting problem that you get is a non-convex optimization problem. It's doubly infinite, as I described, so it's quite a difficult thing to tackle directly. This is known as the primal formulation of the bootstrap, and obviously, in order for us to do something with it, we need to simplify it accordingly to produce a numerically tractable problem. Any questions about this? Cool. Correct, yes, so it's like a parametrization of the plane in terms of. Very good. So what does the modern numerical conformal bootstrap approach do to tackle these difficulties that I just mentioned? First of all, you look for problems where these coefficients C, which are my unknowns, are positive. So there is a large collection of theories, unitary CFTs, for example, at 0 temperature, where this is the case. Then one makes some mild assumptions about the low-lying operator spectrum of that theory. You say maybe my first operator beyond the one that I'm looking for has a gap of, like, I don't know, 2 scaling dimension units and so on. And then you search for a collection of linear functionals that you can construct in this particular way with some coefficients alpha that you apply to this objective function, and you see whether you lead yourself to a something that does not hold, to a contradiction. If you can find even one linear functional that contradicts your assumptions, these assumptions are excluded, and then you start again. So in this way, the following fantastic thing happens. The positivity of these coefficients and the fact that this functional is linear reduces the non-convex problem to one of convex optimization. And there, one can use the power of linear or semi-definite programming to find functionals that violate your assumptions. This is why this is called the dual formulation. Instead of looking for these values directly, you look for functionals, linear functionals that exclude these values. And in that way, you get exclusion bounds for the CFT data. And this has been very, very successful, because if you very cleverly combine not just one crossing equation, but a collection of crossing equations, which kind of mutually overlap, you can arrive at teeny tiny islands where the CFT data can take values, and essentially this determines them to very high accuracy. So the poster child of this approach is the determination of the critical exponents for the 3D Ising CFT to record precision of about 7 decimal points. It is a method which is rigorous. That's why formal theorists love it. If you find a bound, you found a bound. It might not be the best bound, but it's definitely there, and then you can try and improve it. It does require very high numerical precision, sometimes you need to keep track of hundreds of digits in your computations. And it finds many applications in slightly different fields of formal theory. So there is a modern incarnation of the S-matrix bootstrap, where you can use, again, analyticity, unitarity, and crossing to try and constrain scattering amplitudes in various quantum field theories. There is a version of it in cosmology, the cosmological bootstrap, where you try to kind of study primordial non-Gaussianities and inflationary correlators using locality, unitarity, and the symmetries of de Sitter space. There's a matrix quantum mechanics version. There's a modular bootstrap version where you have some CFTs that have modular transformation properties when you look at them in particular spaces, and so on. So very well-loved approach, very successful, rigorous, everyone's happy. Correct, yeah. And this language kind of comes from the kind of computer science language of like primal and dual formulations of an optimizer. The primal and dual formulation of an optimization objective in computer science, yeah. Very good. But there is a big but here. That this approach relies on the positivity of these coefficients. So I said that there's many theories for which this is the case, but not all theories of physical interest satisfy this condition. For example, non-unitary CFTs violate this condition, so you cannot apply this dual version of the bootstrap. Theories that have boundaries, the higher point version of the conformal bootstrap, where instead of getting a crossing equation from a 4-point function, you have a 5-point function, their positivity of these coefficients is not guaranteed. And also, if you put your CFT at finite temperature, which is again of great physical interest, you're not guaranteed that you'll have a positivity of these Cs. In that case, you need to do something different. And our thought was to try and go primal, in some sense, revisit the original formulation in terms of this complicated non-convex optimization and see how far we can go with attacking that problem directly. So for generic problems with large numbers of unknowns, if you try to perform optimization for a non-convex objective function, you encounter the usual problems that there can be many local optima, saddles, minima that have comparable cost. Here we typically will be dealing with optimization over order 100 unknowns, which is quite a high number of unknowns you kind of encounter problems of this type. And for the conformal bootstrap problem that I have in mind, I remind you that we had this additional complication of this equation here being doubly infinite in the number of unknowns and in the number of equations. So we need to perform some kind of approximation for us to be able to put this on a computer. So let me talk a little bit about this approximation. Let's think about a CFT 4-point function where the CFT is at 0 temperature, and by that I mean that I will think about a Euclidean CFT on RD, so a d-dimensional conformal field theory. So there are mathematical theorems that allow you to determine the behavior of operators that are higher up in this sum over here. So you can organize these sums as starting from operators of low scaling dimension. These dimensions are positive. In fact, they're bounded by something known as the unitarity bound for specific spins. And then you can just keep going higher and higher and higher and higher. It's a sum that is, the dimensions are unbounded from above. But these mathematical theorems actually tell you that if you restrict yourself to a particular subset of the domain of your, on your z-plane, you can assess how quickly these coefficients are going to decay as a function of that increasing scaling dimension. In fact, people can prove that these coefficients fall exponentially fast as you increase the scaling dimension. So by performing a combination of restricting the domain of my objective function and also performing a truncation of those sums, I can reasonably well approximate my objective function and attempt to solve it directly. But because of the issue that I'll have with many, many possible different minima and saddles and so on, first of all, the fastest optimizer might not be the right one. You might get stuck on a local minimum. And moreover, we need to be kind of very careful that if we're trying to get results at high accuracy, even very good approximations might not, the minimum that you might find, the global minimum in this approximation of my objective function might not be the one that represents the full problem. Okay. The truncation, say that again, Jim?
Are you assuming that the operator dimensions are bounded?
They are. So your unitarity bound tells you that the operator dimensions are bounded from below.
But you could do non-unitary theories that still have operator dimensions bounded below unitary sufficient.
Yeah. Very good. So the fact that you might have a very complicated landscape for your optimization problem of solutions invites the use of stochastic optimization methods. And one, of course, here has the possibility of choosing over a diverse range of optimizers. Some of these have been used in problems such as this for a very, very long time. And we kind of started investigating what would be the right choice for this particular case. So what we found, maybe in our kind of original naivety, is that a slightly unconventional application of reinforcement learning is something that seems to be doing quite a good job here, and I'll tell you why. So we used a reinforcement learning algorithm known as soft actor critic. This soft actor critic algorithm is one that can deal with continuous state and action spaces, which is what we need in this particular case. It has a reward optimization objective and a kind of entropy optimization objective. So it tries to increase the reward while also acting as randomly as possible and kind of has an exploration goal. And apparently this algorithm that was written with the purpose of being applied to the context of robotics also is quite stable. It kind of ports to different problems according to the authors, and it doesn't require extensive hyperparameter tuning. So let me give you here a map between the reinforcement learning terminology that you are familiar with and the physical problem that we'd like to solve. The environment in this case where the RL agent operates is the set of crossing equations. The action that the agent takes is a choice for the value of the CFT data. So now I've kind of truncated my sums. I can perform either a hard truncation where I really cut off those sums, or an approximation, a soft truncation where I kind of approximate the ones of higher scaling dimension with some in some particular way. Here, let's go for a hard truncation. And my coefficient C. Once the agent has taken this action, the corresponding state that gets produced is the value of these crossing equations for these choices of delta and C. And then finally, I need to construct my reward. The simplest thing that you can do, which is what we did, is to just define the reward as 1 over the Euclidean norm of this state vector over here. And then off you go. You kind of send your agents in this stochastic optimization approach, many of them, and try and see what comes back. So let me tell you how this works in practice for a specific example. I will focus on a one-dimensional CFT. This one-dimensional CFT arises from string theory. So for those of you who know what this is, I'll say the words. For the others, just don't worry about it. In N equals 4 super-Young-Mills, which is a very supersymmetric theory in 4 dimensions with maximal supersymmetry. Some people say that it's the hydrogen atom of the 21st century. It's kind of the simplest kind of supersymmetric and superconformal field theory you can get in 4 dimensions. You can have some defect, which is called the Wilson line. It's a supersymmetric defect. And the theory on this Wilson line is effectively a one-dimensional conformal field theory. It retains some of the superconformal symmetry of N equals 4. There you can insert local operators. These operators are superconformal primaries of the displacement multiplet in this particular theory. Once again, these are details for the people who are experts in this field. And you can construct a version of the crossing equation arising from the computation of this 4-point function. Now, in this case, I can use this correlator and integrate it in 2 different ways to obtain 2 additional constraints on the data that can be used as input for the solution of my problem. So as I said earlier on, in the dual bootstrap, people try to have multiple constraints simultaneously to try and, instead of just getting exclusion bounds for the CFT data, to get these little islands and essentially effectively determine the data that you're looking for. Here we'll do this with having a single crossing equation and these 2 additional constraints. So now you obtain a set of, you have a non-convex optimization problem, you've got these 2 constraints, and then you try different versions of optimizers. I spoke about reinforcement learning as a stochastic optimizer, but you can also try some conventional optimizer. For example, interior point methods we tried, which are very efficient, this IPOpt algorithm. We found that if you take a conventional optimizer, because of the fact that you've got a continuous search space, which is quite wide, if you give this as a box where the search needs to take place in the high-dimensional problem, it's kind of hopeless. It gets stuck in local minima very, very, very quickly. On the other hand, the reinforcement learning optimizer is not as good, and that's a good thing. So what it does is it doesn't see this kind of glassy, structure of your solution space, but it seems to very easily and nicely identify the basin where the true solution lies. So this is an experimental fact. Yeah, so you don't have like this very sharp local minima, yeah, in terms of kind of spin glass, yeah. In terms of non-smooth. So you see what I mean? So you've got something that sort of at large scales it looks smooth, and then locally you kind of see like very deep, very good. So the approach that we ended up doing is to have a pipeline where we first send reinforcement learning agents, a number of them, about 200, to find this, the basin where the true solution lies. And then after we've identified this, we run on this a conventional optimizer, this IPOpt, to really nail down where the solution is. And I should say that the implementation of our reinforcement learning algorithm is such where the size of the box that we give it does not restrict the search to these values. It just restricts the next action that the optimizer takes. So even if this box is small, step by step, it can kind of scan and go over a much larger range of values than a traditional optimizer would see. Yeah.
The idea of using RL is that instead of classical Bayesian also you have the agent is learning from somehow what the Bayesians look like, which Bayesian needs to go to that.
Yeah, I think the idea, kind of very simply, is that it kind of explores a much wider range of of options, I think then the...
This they can also do with traditional algorithms.
Right.
The RL has to figure out something that makes it
Right.
just stochastic.
Right. We found that this combination, when we tried kind of Metropolis Monte Carlo, we tried IPOpt, we tried a few conventional optimizers, and with these large boxes, they were hopeless in identifying the correct solution. So in this particular case, in the example that I'll mention later on, we know what the answer is, so we could actually see whether it's doing a good job or not. Yeah. I should also say that this is an example in 1D. We've applied this method also to two-dimensional CFTs, the 2D easing model, and also the 2-0 CFT in 6 dimensions, which also arises in the context of string theory. It's just a very complicated optimization function. You've got multiple 2F1 kind of, hypergeometrics that depend linearly on these deltas. If you plot this thing, there's kind of many different solutions that you, and think of it in a 100-dimensional space. There's just many different local solutions that can arise. Okay, fantastic. So let me show you a plot. This is the results for the problem that I've just described. We were motivated to look at this particular problem because there was a paper that used the dual formulation to determine the first 3 C coefficients, and by first I mean those corresponding to the lowest dimension operators in this particular problem. The setup is the same. What these gentlemen do is that they obtain, through the dual formulation, these exclusion bounds. And you can see these exclusion bounds for these C's are essentially, in this particular case, it's just a line. Here it starts off a little bit wider, and then it kind of becomes a line as well. So they determine these coefficients in this rigorous way with accuracy, which is up to 7 decimal points. It's a very nice result. In this particular case, the C's depend on a parameter G. This is related to the square root of the 't Hooft coupling in ADS-CFT, so they kind of interpolate from weak to strong coupling in the corresponding CFT in this particular way. On top of that, you see the results from our pipeline that involves RL followed by this IPOpt. And as you can see, for this datum over here, we are really on the money. If you look at the numbers, we also obtain a kind of a 7 decimal point precision with very, very small errors, which are so small that these squares here are larger than the error that you would plot on this graph. In these other cases, our method is not a rigorous method because it's stochastic. We cannot really estimate the error. It might be that the approximation introduces a systematic error. It could be that we have numerical errors as a result of using our particular algorithms. It kind of starts off really well. It goes a little bit out. But in my opinion, if the order of these papers had been kind of exchanged and we first provided these results and then the dual formulation gave you these bounds, I think people would say that this method is producing accurate enough results to at least help and assist the dual formulation to kind of hone down on these particular regions. Yeah, so the relative strengths are the following. I mean, so the first strength, I'll say again at the end, is that there are situations, which I'll turn to, where you cannot apply the dual formulation at all. So in that case, you only have the primal formulation to say again? CFTs at finite temperature, which is what I'm kind of mostly interested in. That's right. And on unitary.
What does it mean to get the result of 7 digits if it doesn't agree with the analytic result?
So in this particular case, it agrees with the analytic result, and this is the one that I was quoting. So I mean, this is just so these people get it to up to 7 decimal points. So there's no analytic. There's a rigorous result. Both are numerical, and they have an error which they can control rigorously up to 7 decimal points.
That's the difference between the solid blue line and the dashed blue line, right? The analytic versus the 7.
So the rigorous dual one are the solid lines, and the points are what we get from this primal formulation.
And dash is the analytic.
So the dash, good, very good. So the dash are the approximations that you compute analytically correct at small and large couplings, so you can do kind of a perturbative expansion around these points.
So if that's exact.
So these are not exact. I mean, you make some approximation, right? So the approximation clearly fails as you kind of go down.
So the solid one is exact.
Correct. That's right. Yeah. Sorry. Yeah. Why not? I mean, you want to go to as high accuracy as you can. I think it's just, these people are.
I'm confused about this curve because you say that
Forget about the dashed line. The dashed line, I mean, this is not my plot. This is the plot of these people. And they wanted to kind of show how the approximations or the expansions that are done at 0 and like at very high 't Hooft coupling is of the order of about 2,500, what these things kind of give you. Presumably there's some issue with approximations that are being done there. Yeah. Yeah, so I mean, as I'll say towards the end, this is with a very basic application of these methods. We have not done extensive parameter tuning. There's improvements that you can do to the pipeline that might actually give better results. We have not, we don't have the resources and time to look at this, but yeah, it's something that could be done. So both of the results that I'm going to show are kind of proof of concept results, which I think are, quite convincing, at least to me, that this is a method that has merit, That's right. Correct. Yeah, that's right. That's right.
Can I ask you a broader question? You asked a lot of questions. So I've talked to a lot of these bootstrap PhD people, Davidson and Dustin.
Sure.
They always argued that machine learning wasn't going to be good for this problem. You need to use these semi-definite programming.
Sure.
And I think the argument is that there's all these local minima and you'll never find it if you just do a kind of...
Very good. So this is a very legitimate
So is that what we're seeing
criticism.
Here,
So the hope that we have is that in situations where the space of solutions that's allowed by the constraints that you're setting is very, very small, the corresponding primal formulation of the problem is also going to fall within these very small values that are allowed. And this is, I think, something that we're seeing over here. So if you don't add this to additional constraints, you can also look at the plots in that case. And then, for example, the optimization kind of sees very different solutions. But once you constrain the values that these data can take, because you've got multiple overlapping constraints, it seemed to be also collapsing the options that the optimizer has in terms of determining these values. So I don't have a very solid thing to tell you. We're investigating this also in the context of the 3D easing model, where you can have 5 crossing equations, and we have some technical problems in trying to implement this method. But the idea here is that if you can get close enough, hopefully you can provide. This is not a method that I would like to replace the rigorous methods that other people are carrying out, but it is a method I think that could guide these rigorous approaches to a particular region, even if it's not accurate to the degree that the dual bootstrap is, to then kind of guide these searches and say, like, now I'm looking at a much smaller range of data that these parameters can take, and then hopefully have an easier job at determining them, if that makes sense. So David Poling, for example, is working on the higher point bootstrap, the 5-point bootstrap, and he's kind of indicated in his recent papers that this approach is an approach that might be beneficial to that problem. Okay, so let me start kind of wrapping up with the second example that I would like to discuss. This is when you have CFTs at finite temperature. So by that I mean Euclidean CFTs on Rd-1 times S1 with a radius beta. This is my Euclideanized time direction, which has been compactified. And these theories are of great interest because they appear in the context of the study of phase transitions, quantum materials, for example, high-density superconductors, and specifically for our interest in high-energy theory, black holes through the anti-de Sitter CFT correspondence. So CFTs at finite temperature are expected to be dual to ADS spaces with black holes in them. In this case, the analog of the crossing equation is called the KMS condition. The KMS condition essentially tells you that these two-point functions of operators have to be periodic as you go around the thermal circle. This is not a condition that these crossing equations, that these two-point functions satisfy automatically, and they start playing the role of the crossing equations that we saw before. So in this particular case, the dual formulation does not apply because there's no positivity of those coefficients C, so you're kind of out of luck. There's no other handles that you have in trying to attack this problem. And moreover, the approximations, if you'd like to try the primal formulation of the problem, the approximations that we made in terms of cutting off those sums and making the problem finite dimensional also break down. So there are no theorems that kind of tell you that these sums the convergence of these sums is fast enough for you to be able to approximate the problem in a numerically tractable way. So it's clear that a new approach is needed along these lines. And this is what we tried to do in a paper which appeared on Tuesday evening. So this is the expression for this thermal two-point function. R and W are just reparameterizations of Z and Z bar. This is my full thermal two-point function, and I'll tell you what's happening here. We have dropped no terms, and I have split here the result for the thermal two-point function in terms of 3 contributions. So let me talk you through these 3 contributions. The third line over here includes all the terms arranged in terms of spin. Each operator has a spin and a scaling dimension. So I have a freely tunable parameter J star, which includes all the operators, let's say this third line, with spin above J star. So here we can use dispersion relations to express the contribution of these terms in terms of this discontinuity of this thermal two-point function. This involves theory-specific input, and in fact, we need to approximate this discontinuity, but it can be done in a systematic way that we have control over. In fact, the more you increase this J star, the better the approximation becomes. For those operators that have spin lower than J star, you split them in terms of these 2 lines. The first one is, again, now with a split in terms of dimensions. Those of low dimension you can write in terms of these thermal coefficients, and then some functions and some dependence on your deltas. In this thermal problem, you make an assumption that you've solved the theory at 0 temperature. You know the dimensions of all the involved operators, and then the only thing that you're looking for are these thermal coefficients, which are scalar quantities. At the same time, there is also an infinite tower of operators with dimension above delta star. And for those operators, we propose to capture them in terms of some functions of this radial variable R on the complex plane. There is one of these functions for each value of J. So in this case, no terms have been dropped. This is an exact expression for the thermal two-point function. And by equating this with the value of the two-point function as you go once around the thermal circle, you get a crossing equation that you're trying to solve. So this is your optimization objective. We have here some functions that we need to solve for. Machine learning and neural networks are kind of natural approaches that you can use, natural tools that you can use to try and find these functions. So we use the pin. My objective function is my crossing equation in this particular case. And a simple architecture seems to be doing the job. In this case, we tried a fully connected MLP. It didn't seem to be doing a very good job, so we tried this multi-branch MLP where you've got just 3 hidden layers, a backbone layer that's fully connected, and then that splits off into these a set of subnets, one for each of these functions that you're trying to determine that captures the low spin but high scaling dimension contributions. The one that we ended up using at the end only has about 10,000 parameters. We use it to perform stochastic runs, about 1,000 runs, and then collected statistics from the best runs. And this seems to be doing a good job in efficiently determining the solution to the KMS condition, as I'll show you in this final slide. So these are results. We can benchmark how well this method performs by comparing against the generalized free field theory. So these are generalized free fields, are fields for which the correlation functions factorize. And there we know the answer analytically. And these are the plots that show you what happens for these tail functions. In this case, our J star was 6, so we have an A0, 2, 4, and 6. For the tail function A4 and A6, the red line that you see there is the analytic solution. The solid blue line is the average of the best performing runs as a result of my pin optimization. And then the bands that you see there is one standard deviation for our results. In these 2 cases, you see it's kind of right on the money. In this case, it seems the optimizer seems to be having a difficult time in splitting the contribution between A0 and A2. But then if you plot the sum of A0 and A2 together against the corresponding sum from the analytic solution, you see that it's again the same. So here you see just a slice of this complex Z plane on the real Z axis. You can also plot here the heat map on the full Z plane, where delta T is the relative difference between the analytic and the solution that we get for this sum of A0 and A2, and the error is of the order of 1%. Great, so this brings me to the end of the talk. Let me summarize what I've said. There's a wide range of problems that can be addressed using the bootstrap philosophy. The dual formulation of the problem is a very efficient and rigorous, especially method that gives fantastic results, but it relies on the positivity of these coefficients C. There are many interesting physical systems where this positivity condition does not apply, like finite temperature or, for example, CFTs in the presence of boundaries and so on. The primal problem is difficult to solve because it involves non-convex optimization, and ML techniques, even in this kind of very rudimentary approach that I showed you here, seems to be a good case in point for investigating such approaches more in the future. The primal problem for the thermal bootstrap using pins can be solved. To my understanding, this is the first time that someone has tried to directly bootstrap a thermal CFT problem. And in the paper, we didn't just compare against benchmark. We also obtained results for CFTs that describe black hole geometries and make some predictions. The optimization obviously can be fine-tuned in ways that can produce solutions with higher accuracy. And the idea is to try and apply now this pin approach to other examples as well. So there's people who use now ML techniques. There's this wonderful paper from last December to the primal and dual bootstrap formulation for the S-matrix problem. The idea here is not to replace these rigorous methods, but to kind of supplement them and kind of maybe guide these rigorous methods once we have results from these stochastic, non-rigorous approaches. And there's much more to do in this space. So I invite people who are interested in this kind of problem to get in touch. There's lots of things to do. We don't have the manpower to do it. And if you're interested in coming to London and working on these kinds of problems, there's many wonderful schemes for bringing people to Europe and the UK, like Marie Curie fellowships, like Newton International Fellowship, sponsored by the Royal Society. Very happy to talk about any of these. Thank you for your attention.
All right, thank you. So we already had a lot of questions, but maybe there's some more questions. Let me come up here.
Thank you for the talk. So you mentioned that you computed like the 4-point correlator between the transverse fields on the Wilson line, the 1D. Yeah. Has this kind of procedure also useful for computing something like a 2-point correlator between fields on the 1D, on the defect?
So these 2-point correlators are fully determined by conformal symmetry when you're at zero temperature. So the first kind of non-trivial correlation function that you get is the 4-point function, which is expressed in terms of the results expressed in terms of the C's and the deltas.
Right, but I'm talking about like defect bulk correlators.
Oh, defect bulk, good, very good. So no, and this is something that I think you can try and do with this approach.
So are there like ideas or something like that? Are there any ideas for doing that, or?
There's many people who kind of, I think are trying to use the bootstrap. I think with the defect, you can probably do it with a dual formulation. If you're interested in terms of like, adding a boundary to that theory, then you need to use these approaches.
Thank you.
Yeah.
Just a basic question about the PINN. In the slide of the PINN, yeah. So do you use each, I remember you have like separated like the small part neo-negro. So do you use each part to model the tail function and coefficient?
Correct, yes.
Okay, thank you.
Thanks for the interesting talk. The use of the RL algorithm as an optimizer sort of, I would say, is a bit unusual. Yeah. And so I guess my question is whether, so RL, right, will at least implicitly learn a policy. And so whether you think that the policy that it learns from the specific optimization, that it can learn something, perhaps that it transfers to other CFT optimization problems. Basically, I want to know whether the RL will learn something, it can learn something about CFTs that we do not know and perhaps could extract.
So in this use of RL, it's kind of a very, let's say, it doesn't make use of the final policy that, once you have reached the minimum, the optimal policy has been learned, then you just throw it away and you don't do anything with it. It's interesting to see if that kind of, transfers to different problems.
Yeah, maybe if the optimizer would get better. I don't know how many of these CFT problems there are that are similar, but if you reapplied them, that would be interesting. Yeah.
This is pretty far removed from anything I've ever worked on, but I was curious with you said you're using RL to avoid this spikiness problem, mm-hmm. But can you not do some form of like strong regularization to avoid that? Because, like normally a loss landscape is super spiky if you have a huge capacity, right. So you regularize it and it smooths it out. I don't know if that's something that makes any sense.
I'm sure there's millions of things that one can try. This kind of numerics is not my kind of background. We tried a few things, but it's not been like at the systematic level that someone who works on these things for a living might do. So very happy to listen to.
Maybe then, maybe it's the answer.
Yeah, maybe it's the answer.
All right, maybe one last question from Jim. Then
My question's fast. I understood a good bit of the ML. I guess in the CFT context, you made the point about finite temperature very clear, but at zero temperature, the dual formulation is the standard thing that people do.
Yeah.
Other than in non-unitary theories, is there some killer application of when you would want the primal over the dual? Because the dual's convex and so forth.
So non-unitary inclusion of boundaries, so bulk to boundary interactions, for example, in a CFT with a boundary.
Okay, so the second you have a CFT with boundary, the dual formulation sort of can't succeed.
Yeah, so thermal theories with boundaries, which are interesting also in the concept of condensed matter.
Yes.
What I was saying on unitary, the three examples. And for the 1D example that I mentioned, we kind of checked with the people who did this work, and resource-wise, we kind of use the same resources. I would say it's kind of, in terms of compute, it's kind of the same kind of approach.
I see. So maybe you want to say the converse, that the dual formulation works when you have a theory without boundaries that is unitary and at zero temperature.
Correct.
But if you break any of those, okay, thanks.
All right, let's thank our speaker again.